Okay. Hello, everyone. Today, I'll talk about zero-knowledge proofs. In the syllabus, I thought I would move into public key encryption and do what we did for signature, so show random oracle arguments and standard model arguments. But the standard model arguments I wanted to show, there are two that I thought we should focus on. One uses non-interactive zero knowledge, and the other smooth projective hash functions. And the second one is a sort of more modern and efficient version, and of the first one in some vague sense. But SPHFs, smooth projective hash functions, are an interesting replacement of zero knowledge, which is cheaper to achieve, and in particular, it's efficient without random oracles. But and of course, it doesn't have this exactly same functionality. It has a weaker functionality, but it suffices for CCA encryption, as we'll see, and it suffices in many other contexts also. But to really appreciate that stuff, I think we should first look at zero knowledge proofs, and then move there as an application. And of course, zero knowledge proofs is one of the fundamental things that we wanted to talk in this class, right? Because it's an ingredient in secure protocols, and an essential one to understand. And also already when you look at it, you will see some concerns of secure computation that are important to keep in mind also in practice, because the concerns will deal with composition, in particular things that are secure in isolation. The arguments will quite clearly fail in the case of parallel composition. And so we will either not have arguments in a realistic case where zero knowledge proofs are used in parallel or concurrently on unlimited number of sessions. I mean, polynomially many, but arbitrary in practice, right? And we'll either see that the proofs don't extend, or that there are actually explicit attacks. In either way, we need you need to be aware of this, and you need to see what can go wrong, and of course how to what are the methods we do know that do guarantee security under arbitrary composition, right? So think of zero knowledge proof used either as part of an encryption, or a part of a signature, or as part of a distributed system like blockchain. And you will see that in all of these applications, or in an authentication protocol, in a key exchange, that parties run multiple instances of these protocols in a massive, on a massive scale. And so our adversary will be able to see concurrent or parallel instances of these protocols. And if you can attack in that setting, that's not good in practice. Okay, so let's introduce these tools. So first of all, we need to have some language for expressing well, a language for language. So let L be a language. So it's a subset of bit strings. And if L is an NP, so it is solvable in a non-deterministic polynomial time, as most problems in computing are. So this class includes efficient algorithms as well, right? And probabilistic algorithms as well. Then there exist efficiently verifiable relation RL such that there exists a pair of x and y in this relation, even only if x is in the language. So we call x a statement. So it's a statement in the language, and we call a w a witness for x in L. So what does it mean that it's efficiently verifiable? So that means that there exists a polynomial time algorithm such that for every xw in RL, the algorithm accepts, otherwise it rejects. Let's give examples. So consider the following language, Hamiltonian cycle. It's a language of graphs G, such that G is a graph which with a Hamiltonian cycle. And what is a Hamiltonian cycle? A cycle through G, which visits each vertex of G exactly once. So you have some complicated graph, right? Like let's say it has n vertices, and n is the parameter, right? So it clears up, and at most n square description of which vertex is connected with which. And your job, so that's a description of the graph, okay? It's n square into number of vertices. And I suppose n square log n, because each of the description is log n size, right? Like you need to tell, because that's the description of the nodes of the graph of size n. And you have that structure, and you have to decide, okay, is there a way to walk through the edges of G and visit each vertex exactly once? Okay. For some graphs, it's an easy decision, right? Like we can see that it's disconnected, right? So we say, no, clearly there's no cycle. For other graphs, it might be hard. And it is, on the other hand, so here a witness W for X in the language of Hamiltonian cyclic graphs is a cycle. It's a Hamiltonian cycle. Okay. So if you actually were given a cycle, right, which were given the description of basically the permutation on the nodes of the graph, such that you can walk through these nodes and you go along the edges of the graph, then verification of XW pair is trivial, right? Like it's a linear walk through the graph. So it's an efficient algorithm. On the other hand, if you don't know the witness, then there are no known polynomial time algorithm. Moreover, this problem is NP complete. So if there existed a polynomial time algorithm that decides whether a graph is has a Hamiltonian cycle or not, then all problems in NP would have polynomial algorithms, right? So all problems are reduced to this. A famous one, right, is the 3-SAT. So this is the language of formulas. Phi is a satisfiable or just satisfiable Boolean formula. Witness W for phi in SAT is the satisfying assignment. Right. So the formula is, let's say the variables are called x1, x2, x3 to xn. Okay. So a formula is some Boolean expression involving these variables. And there is a 3-SAT version, which is simplified. The formula is only a conjunction of disjunctive clauses. And the disjunctive clauses have to have only 3 elements, and one is reducible to the other. So if you can solve 3-SAT, then you can solve SAT, and of course vice versa, because this includes these particular formulas. And if you were given a satisfying assignment, so a function on these xi variables that say x1 is true, x2 is false, x3 is also false, x4 is true, etc., right? So it's then of course you can check in an efficient way that the formula is satisfiable, but finding it, or not a search problem, but just a decision problem, is also known to be NP complete. And in fact, proofs typically go by first showing NP completeness of SAT, and then showing that an instance of Hamiltonian cycle can be presented as an instance of certain formula of size polynomial in the graph, and the graph has a cycle even only if the formula is satisfiable. So these problems are reduced to one another. Another one we might see later when we show constructions for zero knowledge proofs is 3 colorability. So this is it's a set of graphs which are set of vertices and edges, same here, of course, such that, so what is 3 colorability? That there exists a function phi from vertices to 3 colors, 1, 0, 2, such that for all vertices v1, v2 in V, if there exists an edge between them, then the color assigned to V1 must be different from the color assigned to V2. Okay, so that's 3 colorability. You assign colors to vertices so that no 2 connected vertices have the same color. And all these are NP complete. And that means, well, that in particular means that if we show that there exists a zero knowledge proof for one of them, then there will exist a zero knowledge proof for all NP languages. Let's see, give an example of a language that might come up in a cryptographic scheme. It could be many, but here is just one example. Let's say we want to have a language of equal plain text language. Okay, so let's call it EP. Okay, and it will be a language of the following tuples: a pair of public keys and a pair of ciphertexts. And we say that this tuple will belong in the language if there exists a message and some randomness using encryption, such that an encryption of under public key 1 of message 1 using randomness R1 is C1, and encryption of under the PK2 using R2 is C2. Okay. Okay. So, in other words, it's okay. Now, is this an efficient language? So, is there a polynomial time algorithm that can decide this? So, if E is CPA secure, okay, then deciding if public key 1, public key 2, C1, C2 is in this language of equal plain text for randomly generated public keys and ciphertexts, right? So, and these are output by the key generation and encryption E. Deciding whether or not this belongs is equivalent to breaking chosen plain text attack security of encryption. So now NP hardness means that sorry, there's a certain divergence here between standard complexity concerns and what cryptography asks. So for cryptographic applications, what we are usually concerned is not so much the worst case of any PK1, PK2, C1, C2, but the average case. In other words, these inputs are created by randomized algorithms, and we are concerned how the adversary does on randomly generated inputs. But the relation is clear in the following sense. If there existed an efficient algorithm that can do it on every, right, for if this is a if there is a polynomial time algorithm that decides this language, then it will also work on any distribution, right? And so it will work on these random ones, and it will break the crypto system. So what crypto systems ask is actually stronger than just that the problem is in NP. So it has no worst case polynomial time algorithm, but that it's hard on average. Okay. So if you ask, so therefore, if an encryption is chosen plain secure, this language has no polynomial time algorithm, but witness, which is equal to the message and two randomnesses, allows efficient verification. Right? Because you can just recompute the encryption and check. Actually, witness could also be a pair of secret keys corresponding to these PK1 and PK2. And this is the fact that the witness can be, that there could be different witnesses for the same statement will come back to this, because it can be both a trouble in some cases and also a tool that would allow us to argue security. Somewhat maybe think of these signature schemes we looked at last week, where you had the reduction would embed different trapdoors into a statement, and a given adversarial behavior would use different trapdoor embedding to break the underlying problem. You can think of existence of different types of witnesses in a similar way as a potential way to embed trapdoors and let security argument go through. Okay, so as we and there is many many more. One very basic sort of extremely generic one is that let's think that let party P in some in a protocol follow some prescribed protocol pi, okay, and so some party, let's say in an authentication scheme, is supposed to follow this protocol. So it's supposed to take some private keys, some public keys, some passwords, whatever credentials, and perform some action on them. Perhaps create a random challenge, decrypt something, sends the decryption to the counterparty, etc., etc. Okay, and let's say that you can argue that the protocol is secure under the assumption that the party follows the protocol, that everyone follows the protocol. Now we want to say, okay, what about participants who don't follow the protocol? So instead of encrypting, decrypting, signing, whatever, right? With signing you can verify, but some operations perhaps are not easily verifiable on their own. Can you use the proof that argues security in the face of people who follow protocol but just you want to argue what they learn, their view in the protocol does not leak to anything that hide all the secrets that you want the protocol to hide. For example, if a client and a server use some passwords to authenticate, and the server follows the protocol, then you can argue that the client's password is hidden from the server. Okay, so that's so far so good. But what about client trying to authenticate using his password, her password, to a server that does not follow the protocol? But this implies a language of correct execution of pi. It's messages that this party sends in the protocol, such that there exists input and randomness pair, local input of this party. So its password, its secret keys, whatever, and randomness. So randomness using encryption, randomness using whatever the protocol, because the protocol, typically in cryptography, is randomized. Such that M is an output of this protocol pi, given the input and randomness. Okay, and also we should input here the messages that this party receives, right? So that's another part of this input here, but it's a public input. It's well defined. So we're just asking. This is the language of correct responses. Okay, and now you can have you can enforce honest behavior by asking P to prove in zero knowledge, using zero knowledge proof, that its message is in this language, right? And it will be the zero knowledge. Okay, so let's so in general, zero knowledge is a tool that can enforce honest behavior from any protocol. Okay, so that's why it's going to be an incredibly essentially crucial tool, because it's work for any protocol pi, right? Okay, so let's any questions? So let's define a zero knowledge proof for a given language. Definition of a zero knowledge proof. Zero knowledge proof is a pair of efficient algorithms P and V. This is for prover, and this is for verifier. For zero knowledge proof for language L. Okay. And the definition is sort of streamlined for languages in NP, so there exists a efficient verifiability relation RL. Okay, it's possible to define zero knowledge for languages in higher classes, more complex classes, but we won't need them, and generalization is not that hard. So first, the protocol must satisfy completeness. So these algorithms must satisfy the following property. First of all, completeness. This also tells us how to use this zero knowledge proof system. And so in a completeness, we ask that the probability that the verifier algorithm who runs on input a statement, and we count the probability that the verifier accepts, and we ask that it does so when interacting with the prover who has both X and a W. And we ask that the probability is 1, so that it always goes through. There could be some, an error in completeness is allowable too, so it could be relaxed. Okay, and well, first of all, maybe I should. Well, okay, I should have said what the intended syntax of these algorithms is. So the syntax is that the prover works on input X and W, while the verifier works on input X, and they send messages to one another. Okay, so these are interactive algorithms. The prover sends some message, verifier takes it and sends some response. And perhaps the verifier is the first one who initializes, but I have to, say on the picture, this is arbitrary. So in some proof systems, prover will start, in other verifier will start. But the verifier is the one who gets the last message because we don't care about prover's output. But we do care about the verifier's outputs, and the verifier's outputs is a bit, which is either 0 or 1, and 0 is for reject, 1 is for accept. X is, okay, as said before, X is a statement, and W is the witness for this statement. Right, so in the examples that we've seen on the previous slide, X could be says a formula for which the verifier locally cannot, for all cases, right, have an efficient algorithm that does not have an efficient algorithm that would decide whether the formula is satisfiable or not. The prover does have the satisfying assignment and wants to convince the verifier that the assignment is correct, or this tuple of public keys and ciphertext. The verifier wants to be assured that the ciphertext holds the same message, cannot know it by itself if this is a CPA secure encryption, but the prover has witnesses for this, either the decryption keys or randomness used in encryption, and wants to convince the verifier that the statement is true. Okay, and completeness asks that this always succeeds if they have, okay, so completeness is that for every X, for every X in the language, and for every W such that XW is in the relation, right? So for every statement in the language and for every witness that witnesses to the fact that X is in the language, this goes through. So verifier always outputs an accept bit. Okay. The second property is soundness, which is that for all x not in the language, and for any cheating algorithm p star, probability that verifier x accepts when interacting with p star who has the same input x is negligible. Okay, what does this say? This says that if the verifier has a wrong statement, so it is not a satisfiable formula or not a tuple of ciphertexts that contain that encrypt the same plaintext, no matter what the prover does, so arbitrary algorithm can prover can be replaced with an arbitrary algorithm. In fact, honest prover cannot even function, because if a statement is not in language, then the witness does not exist. So presumably the prover algorithm, uses in some way that this is the correct witness. So this algorithm will bomb because it does not have any input. Any other input you put it, the algorithm will, can potentially grind to a halt. But P star is an arbitrary algorithm, right? And no matter what it does, what messages it sends to the verifier, the probability that the verifier accepts must be negligible. So this can be relaxed and even replaced by 1 minus non-negligible suffices. So, you know what? I'm not actually sure. So, make it any constant. Okay. So think of a prover that has some non-negligible probability of convincing the verifier, but this probability is, say, only 1/2. Then that's okay, because the verifier could request that the prover performs this proof 100 times. In each execution, the probability is 1/2, because the coins go over probability over what? Over randomness of V, and well, who else is participating here? It's the randomness of P star. However, because we say for every P star, it's quite easy to see that pick randomness of P star that make this probability the highest. And therefore, once you do that, you don't need to think of randomized P star. It has optimal randomness, if you will. So it's really only this part that matters. And if the probability over random execution of V is that with 1/2 probability, it can be skewed to accept even on a wrong statement, well, when I run it 100 times, the probability that I will throw this bad coin every time is just 2 to the minus 100, right? So basically any constant can be hiked into negligible by sequential composition. And well, it so far it can be, it also works for I think that this would work for parallel composition as well, but zero knowledge does not. So in the context of zero knowledge. That's not so useful. A point here, another point is that we say this is unconditional soundness. So regardless of P star's computational power, In practice, this is an important relaxation, because in practice, you can say, well, who cares that there is some omni-powerful algorithm? I only care about polynomial time algorithm. Okay, because in any case, I'm dealing with crypto systems, so an omni-powerful algorithm would decrypt all my stuff and forge my signatures anyway. So I don't really care about him cheating in a zero knowledge proof if he can break everything else. Soundness might hold only for efficient P stars, cheating provers. And that has a name. That's called. This is called argument. Not a proof. So this would be called a zero knowledge argument rather than zero knowledge proof. Okay, it is just a terminology. In popular parlance, people just say zero knowledge proof, even if it's actually technically only a zero knowledge argument. Okay, so now what is zero knowledge? Okay, of course, that's the property we're all waiting for. And this property says this: for every cheating, so far, right, the fact that it has to terminate with the correct decision for the verifier if the inputs are correct, well, that's obvious. And the soundness property, no way of cheating can convince the other party that the statement is true. What the zero knowledge will be concerned with is what is the privacy property on this witness. Because here is a trivial protocol that is a proof system for NP. Just send the witness over to the verifier, right? You can always do it because you have it. And this will allow verifier to just efficiently decide whether it exists in the language. But think of this application when the statement is a bunch of public keys and ciphertext, and perhaps the witness is the secret keys. Well, I don't want to convince people that encryptions are correct by sending them my private keys. Okay, I don't want in a general protocol to convince people that I'm following the protocol on some inputs of my own. And the way to convince them is to just broadcast what my inputs are, my keys, my passwords, my whatever else, right? Well, that would make no sense, right? In any cryptographic application. So what we want is the intuition behind zero knowledge is precisely that's where it starts. How can a prover convince a verifier without leaking anything about the witness? So can this proof be like an encryption of the witness, so to speak? so that we can argue that it hides everything about the witness, except of the fact that the witness exists. In other words, that the statement is true. And in cryptography, we have a way to model how do you express privacy, secrecy. Well, one would be if encryption of the witness is like our intuition, then let's go with this, because that would mean that you can create the view of the proof, if the proof was essentially an encryptness of the witness, from not knowing the witness. You would like encrypt a random string instead. And if the encryption was CPA secure, then encryption of the real witness and encryption of the random string would be indistinguishable. We somehow must include the requirement that this encryption, quote unquote, also, has this property, right? That somehow it can be used by the verifier to verify veracity of the statement. But the security property will be indistinguishable in style of arguing that the messages sent by this prover on a real witness are indistinguishable from messages which are sent on what is the generalization of encrypt a random string? Well, just follow some algorithm on random inputs. In particular, that alternative algorithm has no access to the witness. And then ask that this alternative algorithm presents a view that is indistinguishable from this one. Just like we ask for encryption, that an encryption of, say, a witness is indistinguishable from an encryption of, say, a random string. So here is how that intuition is, is formalized in the zero knowledge property. That for every cheating verifier star, but here we do ask for every cheating efficient verifier V star, there exists an efficient algorithm SIM, which stands for simulator, such that for every X in the language and every W such that which is a witness for this X, the following two distributions are indistinguishable. Distributions are indistinguishable. Computationally indistinguishable. Okay, well, we'll see how indistinguishable. The first one, so the real is the following, is the view of V star on input X when interacting with P on input X and W. Okay, and let us soon decide what is exactly the view. What do we mean by a view of an algorithm in an interaction? Okay, and the second is the real. So let's call it the real view and designate it as D. And here we will ask for we'll call this one a simulated view. We'll denote it as D prime, and this will be the view of V star. Oh, sorry. You know what? Just output of SIM. on input X. Okay, so in other words, this is a real execution, and this is this alternative algorithm, like the one who, instead of encrypting the witness, encrypts a 0 or a random string because it does not have the witness. And the only thing it has is the public input, which is the statement. Okay, let's see what exactly is the view of the star. Okay, so what is the star's view in an interaction with P? So here is this algorithm V star, and it has an input X, and it generates some messages. Let's say that that V star goes first, okay, and it gets back some response. Let's call this M1. Based on this, it generates some message of its own and gets back message 2. And it recurses, right? Like perhaps it has k rounds. Eventually, this algorithm outputs something. The view was the well, the view was the input, and it was the messages that were sent by P. Note that the messages that V star sends out, so this one and this one, etc., well, it's an efficient algorithm, so they are just some algorithm on the inputs. This one was just on input X. This one was on input X and M1. So these messages are functions of the rest. It's the yellow stuff that basically, once you know what the yellow stuff is, this determines execution of this star. But it does so only if it's a deterministic algorithm, yes? So it needs one more crucial input, and it's the randomness R of this right? It's the local randomness, because without orthogonality, this could be a randomized algorithm to throw coins. Perhaps it's these messages here are encryptions, and V star knows how it picked them, but this P would not know, right? How they're exactly chosen. They're chosen on the input of some local randomness that V star has. So P in here has inputs X and W, right? So what the zero knowledge asks is that the distribution of the yellow stuff, that is the view is V star view is here, well, say X, randomness R, and messages M1, M2, ... sent by P. And everything is some efficient function of the stuff. So without loss of generality, let's just, we don't really care about V star's final output because it's efficiently computed from the yellow stuff anyway. So it is just the yellow stuff. It's everything that V star sees in this execution. simulator on X will need to replicate this view. So it will also generate well, you know what? Let's switch where X is. So it's a Vistar's view on input X, and it's just so we bracket this X, because X will work like a parameter for any X. It is input either to Vistar and also to the simulator, and the game goes on that input. Okay, so in a honest execution, R is chosen at random from however long Vistar, however much randomness Vistar uses, and also P is randomized algorithm, right? So P also has so this is P's local randomness also, right? It's inputted here. And in a real execution, right, like this randomness is chosen at random, prover's randomness is picked, and then they execute. And what the V-star sees is his own randomness and the messages it got from the prover. Simulator needs to create the same thing. So to create a simulator on X needs to also create verifier randomness and the messages, and hopefully these two are computationally indistinguishable. Okay, so that's what's meant by the real view, and so syntactically that's what must be the simulated view for these two distributions to be indistinguishable. Because we are asking indistinguishability here, not that the distributions are exactly the same. So this can be actually, you can ask for perfect zero knowledge, where they are exactly identical. You can ask for statistical zero knowledge, where these would be indistinguishable statistically. So they're statistically close distributions. Okay, the skew between the two distributions is grows down faster than an inverse of any polynomial in the length of this input. And you can ask for computational zero knowledge. In other words, that these two distributions are perhaps statistically very different. They're completely different distributions. One is encryptions of zeros, the other is encryption of ones, but they're not computationally distinguishable unless under some assumptions, right? Like security of an encryption. But you can see that if you achieve this notion, so if the prover execution with a prover is actually indistinguishable from execution with a simulator, then in applications like this, where people who send messages according to some protocol need to then pass, attach, or interact in zero knowledge proofs that that their messages were created correctly. You can ask, okay, does this zero knowledge proof leak anything about the input and randomness of these parties? right? Because this is the private stuff that these parties operate, like their secret keys, passwords, etc. If there exists a simulation procedure that shows that to any party this guy interacts with, the view that this party gets, even if this party is cheating during the zero-knowledge proof, if the verifiers try to extract maximum amount of information from the prover by diverging from the prescribed verifier protocol, it doesn't matter, because whatever they see in this interaction can be simulated knowing only the public input. And what is the public input here? Is this one, the messages that this party anyway sent. So the zero-knowledge proof can be simulated from the statement itself, and therefore it does not leak the inputs, right? So this, in fact, is a kind of a deep statement that the zero-knowledge can work as a compiler from protocol that was secure, assuming parties follow the protocol, so in so-called honest but curious model, to the general model, where you don't have this assumption, when attackers can do whatever they please, and the proof still works in this generic tool of just attaching zero knowledge to your actions, asking everybody to prove in zero knowledge that they follow the protocol. Let's see. Of course, okay. So how to achieve it, right? For a given proof system. You know what? But I know we started a little late, but I think that this is actually a good moment to break, right? So because we have only a few minutes left, so I think, yeah. So we'll take it from next time, and we'll see the proof for actually not a zero knowledge, not an NP language, but for a language that we don't. It's not an NP complete language, but we don't have polynomial algorithms for it. Graph isomorphism. We will have to postpone proof, zero knowledge proof for an NP complete language to later, because it needs extra techniques. But the graph isomorphism language will also tell us how to do a proof of statements like this have a similar structure to the graph isomorphism zero knowledge proof, and we'll use that to see efficient constructions for proofs for many problems that come up in cryptography. Okay. Do you have questions on this so far?
I saw a definition that's a bit different in Goldreich's book. Is it equivalent for NP languages?
Oh, so, you know, so you have to tell me how different, right? Because there is, first of all, you know, we are only here defining for NP languages, right? Because otherwise, statements like this, that there exists a witness, and so what you are comparing, the simulation, the real view, is an interaction with a prover that has a witness, right? So all of this would have to go away if you're considering general languages outside of NP.
Yeah,
that's pretty much syntactic.
From what I remember, he starts by just taking any algorithm P, so not necessarily efficient, and just giving it X. But then later he does something about auxiliary inputs, and then we can give it something, but not necessarily you don't have y w, right?
Yes,
have something
yes.
else.
So if you are considering proof systems which are basically not necessarily efficient, so a prover might be a more powerful algorithm. There is very nice justification for looking at this, right? So in practice, you can ask, well, who cares about provers who are not efficient?
Mm-hmm.
But you know, through a little roundabout route, this does have practical implications. Okay, it's just that they're harder to see. So it's easier to focus on statements which are NP and provers which are efficient. But yes, you can generalize it to general provers, in which case you will basically lose the witness in provers inputs everywhere.
Right. Okay. Thank you.
Okay. There is many other you know, syntactic issues, but actually, so, you know, they appear syntactic and then they actually are important here and there. So we did go over some of these options. You know, which relaxations are sensible, right? We didn't go over all of them. So here is another thing that is not fully formal here in this picture. Already in soundness, when we say it's negligible, what are we talking about? Because negligible is an asymptotic property, and this doesn't seem to have any right parameter embedded into these statements, right? So in order to make this formal, you would have to consider probability which is basically restricted to inputs of certain length. Okay, so think of a length parameter k, and consider all statements which are not in the language but whose length is k, and now this probability, whatever it is, it's some function of k. Okay, and likewise here, because the real view and a simulated view, right? These distributions, when we say they are statistically close or indistinguishable, we have to, these are asymptotic notions. So again, in here too, we implicitly restrict both this view and that one on axes which are of fixed size, call it k, okay? And then the real view is really a view family. For every k, you can okay, yes, hold on, but then yeah, yes, so basically you have to parameter, you have to restrict axis for a certain length, and then go worst case of x for that length.
Couldn't you just take any x and define n as the length of x? So let x be free into language, but the negligible would be with regards to the length of x. Maybe it would be a bit more direct.
Well, you probably get
the same thing. Yeah.
The same thing, but so these distributions, okay, they're sort of parameterized by X, and this one in addition is parameterized by W, right? Because for the same X, there might be many Ws. So, I mean, the proper way to think of this is that think of the worst case X for any length, okay? Because it says that it's for all. And so now you have the real and the simulated distribution for this like worst case X. And you know, let's say you take all X's and you maximize the distance between these distributions. Okay, but you can see that it gets hairy. Okay, so the exact formalism that states both of these as families of distributions, which you know, for any security parameter, you have two views, d and d prime. And what you're saying is that asymptotically, the d and d prime will not diverge except for negligible, asymptotically negligible functions, right? And then you have to, once you see this, then you have to be careful about the relation between the parameter and you know, all X within that parameter, etc. Right? So these are annoying issues that that I didn't. This doesn't, you know, it's not fully formal.
Okay, I think it's the same problem with NP languages, because the witness needs to be you must check it in the size of X, right?
Yes. But that's the nature of this relation, right? So the relation for a language, if even a language is an NP, then the relation, the witness is polynomial in X. Okay,
yes,
so
exactly.
so it's just like you know, that's what it means for a language to be in an NP. There is what is an NP language, right? It takes an input X and it follows non-deterministic choices, but how many? Polynomial time, polynomially many in the input length. These choices, think of them as W. One of them is going to solve the problem, right? So that's the W. And the size of it is polynomial in the input length, or otherwise it would not be not a non-deterministic polynomial time algorithm, right? So that's already embedded in the imposed by the you know, by the fact that this language is in NP. Okay, so I'll stop recording now.